Hello and welcome to the course Design Borefields with Confidence. This is the fourth chapter of this seventh part and we'll be talking about thermal response tests in this chapter. Now, the previous two chapters were more about the methodology you can use in order to design your borefield, to calculate the depth or to calculate the size and the depth. But of course, everything starts with having the right input parameters. And what we discussed already back in part 1 of this course was that the ground properties, of course, are really important when it comes to borefield design, especially the ground thermal conductivity and the undisturbed ground temperature. And we also said that there are databases for these, especially geological departments in each country or each region has some sort of data for this. But yeah, of course, this can change, or there is always some uncertainty on this. Because geology is not that straightforward, it can happen that your own project has a slightly different ground temperature or conductivity. And the only way to know that is by measuring it in situ at the real project location. And this can be done with a thermal response test. So a thermal response test is basically a test you do on an already installed borehole. So you go to your project location, you drill the borehole with the same diameter, the same depth, the same grout, the same heat exchanger as you would do for the rest of your project. You wait a couple of days until the borehole is hardened, the grout is hardened, and it's again in thermal equilibrium with the rest of the ground. And then you install a mobile data logger, which is just a data logger, circulation pump, temperature sensors, and electrical heater. And then what you do is you start heating up the fluid, you measure the in and the outlet temperature, and this you do for 2, 3 or more days. And the reason this test takes so long is because you need to overcome these initial hours where the transient effects, and so the heating of the fluid, the heating of the grout, etc., has gone by. So you want really a steady state heat transfer from the fluid to the ground in order to extract all the required information. And with this TRT test, you can measure the initial undisturbed ground temperature. This you do by simply letting the fluid circulate and before you turn on the heater, and the fluid you get then is the initial ground temperature. You can mathematically, as we will discuss in a second, extract the ground thermal conductivity as well as the borehole thermal resistance. Now, this borehole thermal resistance, I placed a star next to it because yes, you can get this mathematically, but it's not always a good idea to use this value directly for your design. We discussed already many times that the borehole resistance, it depends on your type of antifreeze, your flow rate, your temperature, and so forth. And typically these TRT tests are done with pure water. So if your case has an antifreeze added to it, your viscosity will be different and hence will your turbulence and also your borehole resistance. So please be careful when using the measured borehole resistance for your design and make sure that the value that's actually measured, so the conditions by which the borehole resistance was measured, is actually representative for your actual design. If it's not, please just use the calculate the borehole resistance in GHEtool directly. Now, how does this thermal response test work? What's the mathematics behind this analysis? And that's a very complicated formula. And basically, it's based on the line source model. So a borehole is assumed to be a line, and we express the average fluid temperature in function of quite a lot of parameters. There is the ground thermal conductivity there is the borehole depth, there is the injection power, there is the ground thermal diffusivity, borehole radius, and so forth. So it's a really, really complicated formula. But if we take just a closer look at it, what we see is that we take the same formula, we have this factor, and we have this whole other factor. And we can simplify this equation into a simple linear curve where we say the difference between the fluid temperature and our initial undisturbed ground temperature, it's the Tf minus T0, is equal to a linear function with respect to the logarithm of time. Now, what does this mean? Let us take a look at some graphs. Because here we have typically the temperature that's being measured, and it behaves like a logarithm. So it goes steep up, that's the transient zone, this initial period, and then afterwards it goes off more or less as a constant. And it's here where we can actually do the analysis. So if we convert this graph, which is now in linear in fluid temperature and in time, we take it to a logarithmic scale. You see that the curve changes shape, and that after, let's say, 6 hours or something like that, the line is exactly linear in this semi-logarithmic scale. So now, instead of having the x-axis go from 0 to 50 to 30 to 45 to 60 hours in constant intervals, now we always go with a factor of 10. So from 0 to 0.1 to 1 to 10 to 100. So that's the concept of a logarithmic scale. And it's this linear logarithmic approximation that can actually be used to determine all these parameters. It is to say, if we extrapolate this line and see where it crosses the y-axis, that's exactly this m. It's basically how the line is shifted upwards. And then we have the slope of this line, and the slope of this line is actually the k in the formula below. And once we know this k and this m value, we can actually use that to reverse engineer using the detailed formula we saw on the previous slide to come up with the ground thermal conductivity as well as the borehole resistance. Now, over in the textbook, you will see that there are other mathematical ways of doing this. You will see that there are different ways of doing thermal response tests, not only with a constant power, but also with constant temperature or constant temperature and power and so forth. So there's quite a lot of innovation in it, but this is typically the most common. So let us jump into GHEtool and see with a real life example how you can analyze the thermal response test. So here we are again in GHEtool, and now we'll be using the analyzed thermal response testing. So let's go ahead and click this and go to TRT data. So for every TRT test, we need to fill in some general parameters. First, we need to fill in a value for the ground volumetric heat capacity. Now, in our case, in our measurement, it was 2.25, but typically this is an estimate you have to make, because mathematically speaking, your TRT test cannot determine both the volumetric heat capacity and the thermal conductivity. But since the uncertainty, let's say, on the volumetric heat capacity is typically smaller, this one is the one that's estimated based on data sheets available for your own geology. There are also more complicated mathematical analysis methods that do not need this estimate, but this is not very common, and it's again described in the textbook. A borehole diameter is also an input. It was 152. The borehole length was 193.5 meters, and the undisturbed ground temperature was 14.7 in our case. Now, if we go ahead, this was the measurement data. It's a case well described in literature. So we have the seconds, all the measurements. It was in minutes intervals. We have the average fluid temperature. So it was already average between the inlet and the outlet. And we have the ejection power also every minute. Now, I want to draw the attention that in this case, the measurement does not start at 0. And that's what I said, that these initial hours, the fluid or the system is not a steady state, so it was cut away. And if it was not cut away, you can select in GHEtool at which line you actually want to start with the steady state, so where the graph was exactly linear in this semi-logarithmic plot. But in our case, it was already cut away. So let us go ahead to GHEtool and say select the measurement data. I will go to my measurement data. Again, if you want to do this, it's in the textbook over on our website. And then we have some input options. So is the power included? Yes, it was. There was a separate column for the power. And what was measured, was it the average fluid temperature or the in and the outlet? Can be different for your particular case. In our case, we measured the average fluid temperature, or that's at least what's in the CSV. And our steady state, it already starts at index 0, so the first line. If that's not the case, you can change it here. Then I have to say the time is in seconds. The power is the power column. It's not in kilowatts, but in watts. And then the average fluid is in degrees Celsius. So let us go ahead and import this, and then we can calculate this TRT send it to the server, and we will get back an answer very soon. And that's exactly what we see here. This is our semi-logarithmic scale. So you see 1, 2, 3, 5, 10. And so our logarithmic scale in hours. You see our temperature. And you can see that it's very linear in this case. Perhaps this beginning, you can see this slightly going upward slope. So it was perhaps not quite steady state. But anyhow, it's now a constant line here. You see here also the regression with our K and M, here called A and B value, as well as the average calculated thermal conductivity of 2.27 and a very good borehole resistance of 0.06. So that's basically the TRT analysis. Now, you can go a little bit further and also look at the convergence. Now, what does this mean? I said that a TRT test typically takes 48, 72, in this case, even 80 hours. And how do you know if a TRT test was actually long enough? Well, that's by looking at the convergence data. And what this does is, for the case here, we see 10. This means that if we consider the first 10 hours, we have an average ground conductivity of 2.3. If we consider the first 20 hours, it will be 2.25 and so forth. And basically what you want is that the more measurement data you consider, so if you consider the whole 90 hours, that it's going constant, that it becomes a constant. Because if your curve does not converge even after 100 hours or something like that, there is a chance that there is, for example, groundwater flow and so forth messing with your measurement. So in this case, you see it goes down quite fast and then it's more or less constant. And also a borehole resistance, yes, it fluctuates a lot, but you have to see look at the absolute values. It's rather minimal. So that's how you should interpret your TRT convergence data. So in this case, the TRT measurement is rather good, and these are the values you can use to actually design your system. So this was what I wanted to say about thermal response tests, what they are and how you can analyze them in GHEtool. And I hope you found this interesting. Please try out the exercises at the end of the chapter to learn more about it. And I'm looking forward to seeing you first in the answers to the questions and then in the next part.